Hi everyone. So in this video I'm going to take you on an adventure of past paper questions. These are section C form questions. A little bit complex but very easy for us to understand. So this is a redox titration question, as you can see. So these are the questions that we have. We need to tell the color change at the end point, and then we need to complete the table. We need to determine the titer volume, of course, and then be able to determine the percentage purity. Question 2, another question from a past paper. This question is also on titration, not very different from the previous one. Then question 3 is also on titration, um, except this one is a little bit different. You'll be able to see. So redox titration, and then we've got potassium permanganate, and then reacting with the iron tablets. Okay, so there are questions that we need to answer there. We need to state the color change, we need to determine the number of moles, so all lying in titration, the concept of titration. And then question 4, this is a question on back titration, so we should be able to answer all these questions at the end of this video. Okay, so hopefully this video help you build confidence as you approach your exams. Let's just get into it. Stoichiometry based questions. Alright, an experiment was carried out to determine the purity of solid carbonate, sodium carbonate of course. The following procedure was used. 4.89 grams of impure sodium carbonate was weighed and it was dissolved in distilled water. The solution and washings were transferred into a 250 cubic centimeter volumetric flask, and the liquid level made up to the mark with distilled water and the flask shaken. A pipette was used to transfer 25 cubic centimeter portions of the solution to conical flasks. Each portion of the solution was then titrated with hydrochloric acid of concentration 0.200 molar decimeter cubed. This is the equation of the reaction. Then the first part is the indicator used as methyl orange. State the color change at the end point from dash to dash. Complete the table and using appropriate titrations and calculate the mean titer. Okay, so this question looks too complex to just understand, get the context at once. So we are going to break it down step by step. So I want you to pay particular attention to the question. Let's start over. Now we've read the question, we've gotten at least what they require us to answer, right? So ideally, I'll summarize it using this equation. Okay, so we've got an impure sodium carbonate. Okay, so by impure we mean it has got unwanted substances. Okay, it's not pure sodium carbonate. So what do? We decide to weigh. We determine the mass of the sodium carbonate, which was 4.89 grams. So we know the mass of sodium carbonate. And then what do we do after we've weighed it? We dissolve it in distilled water. So we dissolve it in water, and then after that the solution and all the washings are then transferred to, so that's a volume. Okay, because the question says and the liquid level made up to the mark with distilled water, so there is all that. So that 4.8 grams is dissolved and then made a solution of up to 2 big centimeter was made. Okay, so after that what do? And then you decide now, okay, you get a pipette is now being used to transfer from that volumetric flask. Okay, to transfer 25 cubic centimeter portions of a solution to conical flasks. Okay, and then each portion of those portions are then titrated with hydrochloric acid, and these were the results. So you've got about 4 burettes. Okay, you've got 4 burettes, and then each of them with these as starting readings, and then the final readings after titrating are those ones there. Okay, so just to give you a little bit of some imagery of what's happening here. So you've got, let's say this is a solid 4.89 grams of sodium carbonate, and then you decide to dissolve it. You dissolve it to produce a volume of up to 250 cubic centimeter volumetric flask. Okay, maybe something like this. Okay, so up to 250 cubic centimeters. Okay, then what do? You decide to use a pipette now to make some transfers to the burette. Okay, I have to be very careful here. No, you decide to make portions to conical flasks, so you put them in conical flasks. Okay, um, like that. So there are four of them, actually, four of them. So these are 1 and 2, and then in your burette, that's where you have your hydrochloric acid. Okay, that's where you have hydrochloric acid, four of them as well. Okay, so this is just the image of what's happening. So you get the 4.89 grams, you dissolve it in distilled water up to a volume of 250 cubic centimeters, and then you use a pipette to get from the volumetric flask, and then you put in these conical flasks, and the volume that you're putting there is 25 cubic centimeters each. Okay, and then you begin now titrating it using what? The hydrochloric acid that is contained there in the burettes. And this 250, you have just gotten four of them, right? Okay, so this is exactly what's happening. Now the readings that are given in the table are the readings that you are seeing on the burettes. So in short, they will be able to help us determine the volume that was required by these portions that were gotten. So the indicator used was methyl orange, and now we need to state the color change at the end point. So what are we doing? What we are doing is we are adding an acid, right? We're adding an acid to the sodium carbonate. Okay, so what do you think was the color change there? What do you think was the color change? So you need to understand now these indicators, and I'll give you a little bit of some summary, just so that you can just but the simple answer, let me give you the simple answer, and then I'll give you some explanations on what happens to the other indicators. So this is going to move from yellow. You're moving from yellow to red because you're ending up with an acid. Okay, this is for methyl orange. And just a bit of some context when it comes to these indicators. Um, Starting with the same methyl orange. So methyl orange, its color in an acid, when it comes to an acid, its color is red, and that's why we ended up with red. But in a base, it's yellow. Okay, so we were adding an acid, so that's why it moved from yellow to red. For phenolphthalein, in an acid, so if we actually use phenolphthalein, it's supposed to end up colorless because it becomes colorless in what? In an acid, and then it's pink in the base. Okay, so let me just mention about these two. Okay, now we can move to the other part of the question, which says we need to complete the table and be able to determine the mean titer. I've done a lot of talking. Yeah, but I hope you're getting, because I want to give you quality explanation, so that when you face an exam, you know what we're talking about and you know what we're dealing with. Okay, so when it comes to the volume of the hydrochloric acid that was required, you just need to look at the start and the final readings of the burette, and so yeah, just subtract. So the final minus the initial, final minus the initial, final minus the initial, and yeah. So let's start with the first one. So 27.55 minus 0, that will just remain 27.55. 26.25 minus 0.05, that's just 26.20. 28.30 minus 1.05, that's going to give us 27.25. And finally, 26.15 minus 0.05, that will give us 26.10. So when you say determine the mean titer, the mean means average. So how many of these did we have? We had 4 of them. So we're going to add them and then divide by 4. So 27.55 plus 26.20 plus 27.25 plus 26.10. These are 4 measurements, and then we divide by 4. Okay? So the total value that we're going to have, or that we're ending up with, is 107.2 divided by 4, which gives us 26.8 cubic centimeters. This is the mean titer. Okay? So mean titer, it means this is the average volume of the acid that was required by the portions that we had collected in our flasks. Okay? Now, C says we need to determine now the, let's just take note of the mean titer. That's 26.8 cubic centimeters. Now we need to determine the percentage purity by mass of sodium carbonate. I told you what we started with was an impure mass of 4.89 grams. Okay. Now, for you to be able to determine the percentage purity, you need to determine the mass of the pure one. Okay. So the one that takes part in the reaction is the pure part of it. Okay. Now we have to be smart about this. We've determined the amount of acid that was required by the 25 cubic centimeter portions of the solution that was formed from the 4.89 grams. Okay. So let me take you back to this. So I said we had 4 of these, each 25 cubic centimeters. So we've determined the average volume of the HCl in the burette that was required. Okay. What have we said? We said they require on average 26.8 cubic centimeters of what? Of the hydrochloric acid. This is required by 25 cubic centimeters of the sodium carbonate. Okay, which is just a representation of the 250 that we had come up with after diluting the 4.89 grams. Okay, now can we find the mass of the pure sodium carbonate using the volume of the acid that was required? Okay, this is now where we get back to the equation. Okay, we'll see that these guys are in the ratio of 1 to 2. Can we find the number of moles of hydrochloric acid? Okay, now if we go back to the question said each portion was being titrated with hydrochloric acid of concentration 0.20 mole per decimeter cubed. So the other piece of information we are given is the fact that the hydrochloric acid was 0.2, okay, moles per decimeter cubed. Okay, that's one thing that we know again. So we know the concentration, we also know the volume of the hydrochloric acid required by 25 cubic centimeter portion of the diluted sodium carbonate. So we can find the number of moles of the hydrochloric acid by multiplying the concentration and volume. So the concentration was 0.2. Let me just write that properly. There's not enough space there. So 0.2 moles per decimeter cubed multiplied by 26.8 cubic centimeter, which we can divide directly by 1,000 so that we can have it in decimeter cubed as a volume. Okay, so 26.8, it becomes decimeter cubed when we divide by 1,000. Okay, so the number of moles 0.2. So I'll start 26.8 divided by 1,000 and then multiply by 0.2. So that gives us 5.36 times 10 to the power negative 3. These are the number of moles. Now These moles are the number of moles contained, or these are the number of moles that were required by just 25 cubic centimeter. Okay, that's one thing that you need to know there. The mean titer is just a representation of an average value that each portion of the 4 requires. So in essence, it's just required by 25 cubic centimeters. Now, if we take it back to the question, we had diluted up to 250 cubic centimeters. Okay, after we dissolved the impure sodium carbonate. So if these are the number of moles that are contained in a 25 cubic centimeter, how many moles are contained in the 250? Okay, so it's just a simple ratio, basic ratio that we're actually making there. Okay, so let's do that. So if we are saying in the 25 cubic centimeters we have 5.36 times 10 to the power negative 3 moles, how many moles do we have in the original 250? Because we're just using these portions to help us perform the calculations easily. Okay, so we can cross and multiply. That would be 25x is equal to 250 250 multiplied by that 5.36 times 10 to the power negative 3. At the end of the day, what we're doing is just multiplying by 10, right? So multiply by 10, what you get is 0.0536. This is the number of moles. The number of moles of what? These are the number of moles of the hydrochloric, not hydrochloric acid. I think this is where now we are messing up again. I've seen where I've messed up. This number of moles that we are determining here are the number of moles of the hydrochloric acid there. Okay. Okay, so we've determined the number of moles of the hydrochloric acid that was required by 8.5 cubic centimeters of what? Of a portion of the 4 portions that were gotten from the 250 cubic centimeters. Okay. Now, if we go back to our equation, we should be able to determine the number of moles of the sodium carbonate by using the balanced equation. So these guys were in the ratio of 1 to 2. 1 to 2. So 1 to 2. So the sodium carbonate against the HCl, these guys are in the ratio of 1 to 2. Okay. So 1 to 2. So we've determined the number of moles that were required by 8.5 cubic centimeters of sodium carbonate. So that's going to be, we don't know the number of moles of sodium carbonate, but we've determined the number of moles of hydrochloric acid, and that is 5.36 times 10 to the power negative 3. This is what was required by 25 cubic centimeters of sodium carbonate. So we can find the number of moles present in the 25 cubic centimeters of the sodium carbonate that was contained in the flask, the conical flask. Okay. So if you see this, you see that actually it's just going to be half of that. So 5.36 and then to be divided by 2, that's approximately 2.7, right? So 5.36 divided by 2, 2.68 times 10 to the power negative 3 moles. These are the number of moles of what? These now are the number of moles of sodium carbonate. I think I need to make that clear there. These are the number of moles of sodium carbonate. Okay. Now these are the number of moles present in a 25 cubic centimeters, because that's the amount that was being used in each portion to titrate against this acid. Okay. So this is just a representation of the 250. Now, how do we find the number of moles that we are present in the O250 cubic centimeters? I think it's just a basic ratio. If you compare 25 to 250, that's like 10 times, right? So whatever you have in 25 cubic centimeters should be 10 times in the 250. So this 2.68 times 10 to the power negative, you can just multiply by 10. If you want, you can draw the ratio like I have. But at the end of the day, you're just going to multiply by 10 because it's 10 times. So 2.68 times 10 to the power negative 3 times 10. Okay. Times 10. That gives us 0.0268 8 watt. This is moles of what? Of sodium carbonate. So we've determined the number of moles of sodium carbonate in the O250 cubic centimeters by using titration. Okay. Now after this point now, you should be able to find the mass, right? You just now need to look at the sodium carbonate and determine the molar mass so that you find the actual mass of a pure sodium carbonate so that we're able to determine the purity. So yeah, grab your periodic table now. It's time to use your periodic table and estimate the molar mass of sodium carbonate. So I believe sodium is approximately 23 times 2, carbon 12. So use your periodic table to do these calculations. 2 times 23 plus 12 plus 3 multiplied by 16. So approximately the value is 106 grams per mole. Okay. So try now to find the mass. So you know that number of moles is mass over molar mass, right? So when it comes to determining the mass, it's just a product of the molar mass, which is grams per mole. So you say the 106 grams per mole multiplied against the number of moles, which is 0.0268 moles, and then the moles, of course, will just end up dividing, right? So that you just ultimately remain with the grams. So times 0.0268, that gives us 2.8408 grams. Okay, that's the grams. So we have a grams now of a pure sodium carbonate that had taken part in the reaction. Now the implication is the rest of it wasn't pure, it was impure. The impure one was 4.89 grams. Okay, so times 100 now. So let's see now. That value divided by 4.89 times 10 times 100, sorry, that's going to give us 58.09%. And if I go back to the values that were given, I think the least number of significant figures was 25, so this can just be 58%. In summary, with all the issues that we've done here, in summary, it's important for you to take your time when you see these questions and allow yourself to think. That's why it's important to have solid foundations and understanding of these concepts one at a time. And so the key things that I've indicated here is I demonstrated the fact that I'm able to understand step by step the steps involved in titration, and I'm able to picture what used. Okay, the instruments, I know what a burette is, I know what a flask is, so I'm able to create that imagery on my mind about the whole process and picture and step by step connect the dots on how to navigate through and get to a point where we even get to the stoichiometric calculations. Okay, so that's it to this question. And yeah, so let's move. Question 2 now. A student performs a titration to determine the concentration of a 1 liter solution of sulfuric acid. So for those of you who want to access all these questions and also be able to access our site to learn stoichiometry in full and all the other topics in chemistry, use the link in the description below. On that site, you also find quizzes, past paper questions, and also tutorial sheet questions to help you build your confidence and just grow your understanding of chemistry. So, yeah, see you on the other side.